My name is Rick Mohr, and I'll be talking today a little bit about trying to understand Lustre timeouts. Just a quick overview. Lustre uses timeouts in several places as a way of detecting problems and ensuring forward progress for the file system. It includes things like, detecting packet loss on the networks, as well as preventing a crashed client from blocking I/O because it's stuck holding a lock. There are quite a few places where timeouts are used in Lustre, and there's too many for me to go discuss them all in detail. So today, my goal is to try to touch on some of the most relevant timeouts that are used. I'm going to try to describe the purpose of them and relationships that some of these timeouts have amongst each other. So full disclosure, I'm not a total expert in Lustre timeouts. The information I've got here has been it's an accumulation of knowledge I've gotten from the Lustre manual, from digging through source code, talking with my coworker, James Simmons. I will do my best to answer any questions you may have, but I'll depend on other Lustre experts in the audience to either answer questions I cannot or to correct any misstatements I might make. So timeouts can be roughly divided into two groups. You have what I call Lustre timeouts and the LNet layer timeouts. Timeouts at the Lustre level are primarily focused on ensuring that RPCs complete in a finite amount of time. These include things like bulk data transfers, granting and revoking locks. These timeouts are responsible for things like client evictions. They also occur in other places like imperative recovery. These are the kind of timeouts you'll often see printed to the console. The other group is timeouts that operate at the LNet layer. Those are primarily focused on ensuring point-to-point communications get completed in a finite amount of time. You have some that are LND specific timeouts that depend on the type of fabric you're running. You also have some that are more general LNet transaction related timeouts, and timeouts that are related to router health if you happen to run Lustre in a LNet routed environment. A lot of these timeouts are not necessarily printed to the console, and some of these have to be enabled by adding the net error, which you can do with like a LCTL set param to print K. So to start out, I'll start sort of at the top level and go from Lustre timeouts and then discuss the LNet layer ones at the end. So I'll start with adaptive timeouts. This is something that Lustre enables by default. What happens is that servers track the completion times for various RPCs, and they report that information to clients to give them an estimate of how long they think a request might take. This information is tracked on, not just for all RPCs, but rather it's split up by the types of RPCs as well. So it makes a distinction between the time estimates for different types of requests that come from clients. These can dynamically change based on system performance. So the Lustre servers will update them. And in instances where a server might be getting bogged down, the request is taking longer than normal, there's the ability for servers to send an early reply and basically inform the client that, hey, I know I told you it was probably going to take this long, but it's actually taking longer. Like, don't worry, nothing's wrong. I just need a little more time to get this completed. And then the client can extend the timeout value on the request. Now, since these timeouts are sort of dynamically determined, there aren't a lot of parameters to tune for this. The three parameters you're likely to see are ATmin, ATmax, and the LDLM in QMin parameters. There are a few others that control things like the time increment that's used for early replies, the time window for which the servers will track the request history for the timeout estimates, things like that. But by and large, the default values for these probably will work for most people. So two of these timeouts, ATmin and ATmax, those are the values that determine the size of the window that are sort of lower and upper bounds. So when a server replies to the client saying, I estimate this much time for the request, These two parameters will basically say the server will never return an estimate less than ATmin and never more than ATmax. So the ATmin, the thing to keep in mind is this isn't actually the amount of time that the servers will take to process the request. That's just the smallest value a server will send. So if you set that to something like 40 seconds and requests are completing with 2 or 3 seconds, the server's estimate will always be 40 seconds. It will never go lower than that. Now, there can be benefits to increasing this timeout for things like transient issues. If your system is replying quickly, requests are being processed very fast, but you know that there could be certain instances where, Fabric gets rerouted, a server fails over. There could be times where the time it takes to do that could go beyond what historically has been the amount of time it takes to complete the RPC. In most circumstances, then the client would use its estimate and determine, oh, something's wrong, this request took too long, it's going to time out. But if you increase the ATmin value, you can basically use it as a buffer to say, well, never give an estimate lower than 10 seconds. So if one of these instances happen, it can basically sort of absorb that. The client will have a value that gives it sufficient time for, say, the Fabric to recover, and the client won't necessarily consider it a timeout and sort of error out the transaction. ATmax is basically the upper limit for any service estimate. And in that case, if that timeout's reached, that's considered a failure. The RPC for Lustre will time out if the time window hits the ATmax. Lowering this value can be useful if you want to detect problems faster. If something goes wrong, requests will time out quicker, and you might get notified that something's happening. But you need to be careful about setting it too low, otherwise you're just going to get spurious timeouts, fairly, periodic minor slowdowns that aren't necessarily indicative of a hardware issue could end up then causing all of these timeouts for your RPC requests unnecessarily. And if you set ATmax to 0, that's a way of disabling adaptive timeouts. The third parameter to LDLM enqueuemin param is the minimum timeout to enqueue a lock request. Lock requests in Lustre can be more complicated than other RPCs. If a client requests a lock that's held by another client, then the server has to go through the process of contacting the other client, telling it, I need your lock back, giving it time to complete any IO requests that are outstanding, return the lock, and then notify the new client that it has received the lock. So as a result, using a minimum value for this that matches like ATmin doesn't necessarily make much sense, because those requests could be much more complicated than a simple bulk IO transfer. And so they use this parameter to set that minimum. And you notice the default value of this is 100 seconds compared to the default value for ATmin, which is 0 seconds. Now there are commands that you can set these values. You can query historical info about what timeouts have been seen for various requests. And I won't go into those commands here. Those are given in the Lustre manual. They're pretty easy to look up and find the information if you need it. Now, if you choose to disable adaptive timeouts and go with static timeouts, those are primarily controlled by two parameters. The first being the aptly named timeout value. This is if you do, like you did, LCTL set param timeout equals, this is the value you would be setting with that. That's the time that a client waits for the server to complete an RPC. Sometimes it's referred to as like a master timeout, or called the OBD timeout, because that's how it's identified in the Lustre code, as the OBD timeout variable. And it's the value that's used to calculate a lot of other timeouts that appear in the Lustre code. The other static timeout is the LDLM timeout, and that's the time that the server waits for a client to reply to a lock cancellation request. And by default, that's 20 seconds for an OST, 6 seconds for MDS. And this list gives you an example of some of the other timeouts that are sort of derived from that OBD timeout. You'll see things like imperative recovery is 4 times the OBD timeout. You've get for a lock completion AST timeout is the same as OBD timeout, but a blocking AST timeout is half of the OBD timeout. And then you've got things like OBD ping interval. That's set based on 1/4 of the OBD timeout. The portal RPC health check ends up being 1.5 times the OBD timeout. And there's a watchdog timeout that's like 10 times as much. You can see like everything is sort of scaled in relation to this OBD timeout. And as a result, you can kind of see where the strength comes from using adaptive timeouts. If you have a system and you needed to tune something, it becomes harder to fine tune these things. The only parameter you have to control is really like the OBD timeout. So if you want to change the ping interval and increase it, you have to increase the OBD timeout. But that means you're also increasing lock completion, AST timeouts, and various things like that. They're all related. So to change one to suit your needs also means changing others, which could potentially not have the effects that you desire. And so that's where the strength of the adaptive timeouts comes in at. As far as the static LDLM timeout goes, the portal RPC requests set a static timeout based on the LDLM timeout and OBD timeout. It's actually the min of LDLM timeout and 1/3 of the OBD timeout. And there are some restrictions on setting this value if you choose to do it. First of all, if you set it to a value greater than the OBD timeout in the Lustre code, it will actually just turn around and set it to 1/3 of the value. So in fact, there doesn't appear to be any reason to set this more than 1/3 of the OBD timeout. And this value itself is really not so much used directly to set timeouts for things, but more as a way of sort of setting boundaries for what the timeouts are. And there's a timeout for bulk I/O that, as far as I can tell, is not documented in the Lustre manual. You can actually retrieve it with lctl get param, and the default value is 100 seconds. If the deadline goes beyond it, then if the deadline set in the RPC request ends up being greater than the bulk timeout, then the bulk timeout value is used instead in the code. So this seems to set a hard limit on the time for bulk I/O, regardless of how you might tune some of the other parameters. But when this happened, the Lustre code, as far as I could tell in the request itself, even though it compares it to the bulk timeout to determine if it's greater, it doesn't actually change the deadline in the RPC request itself if it does exceed the bulk timeout. Now, going a little bit deeper below the Lustre layer, you get down to the LNet layer, where you deal with networking related timeouts. Now there's sort of the general LNet layer itself, the part that's not LND specific, that doesn't really isn't changed based on like the fabric you're running. It's just sort of the generic LNet sort of infrastructure code layer. Here there's only really a couple of values of timeouts that occur. If you look at this code, you'll see that there's a LNet transaction timeout, which defaults to 150 seconds. This is something it really serves 2 purposes. It's messages are dropped if they haven't been sent by the time this timeout expires, if they're still on there and the retry count hasn't been reached. And it also comes into play if a response is expected, but their response has not been received within this timeout, then that message is considered to be dropped. The Lustre manual, I believe, states that the default here is 30 seconds, but that doesn't seem to match up with this code, so I think the Lustre manual is a bit out of date there. The other timeout is LNet LND timeout, and this is not something you can independently set. It's simply derived from the LNet transaction timeout. And I've listed the formula here of how that's determined. This differs a bit from the Lustre manual too. The Lustre manual says that it's basically the LNet transaction timeout divided by the LNet retry count. But I believe there was, not too long ago, there was a ticket submitted that caused this to be adjusted. I think the intent was to ensure that the LND timeout was small enough so that you could actually get all of the retries necessary within the LNet transaction timeout window. So that's another place where the Lustre manual seems to deviate a bit from the code. In a routed environment, there's also a set of timeouts that you may be familiar with related to determining LNet router health. In that environment, you'll have nodes that they'll periodically ping LNet routers to track whether they're alive or dead, to determine whether they should be used to send requests through to the other side, to other LNet networks. And the frequency of those pings is controlled by your live router check interval and dead router check interval parameters. If a reply is not received, and there's a parameter router ping timeout, and if that defaults to 50 seconds, and if a reply is not received from a router in that time, that's when the node considers the router dead. And in general, this timeout should be consistent with the LND timeout. You definitely don't want to set a router ping timeout that's smaller than the timeout you'd expect on the fabric itself. If the LND timeout is increased, you may need to also increase your router ping timeout. And below the generic LNet layer is when you get to the LND specific stuff. These are the drivers that are specific to the type of fabric you're running. I'm not going to try to go into all of them. I will touch on just one, KO2IB LND timeout, which you'll be familiar with if you run an IB fabric. And it basically has a timeout parameter for that specific driver that says tells it how long to wait on transmissions before considering them to be failed. If it's not specified, the value will be set to the LNet LND timeout that I shown on the previous slide. This is a case where the generic LNet layer sort of sets a value for it, and if the LND driver doesn't choose to override it with its own value, it will take that generic value from the LNet layer itself. Setting the timeout lower can help you detect problems sooner because the request will time out sooner, but once again, like most of the other timeouts, setting it too low can lead to spurious timeouts if you get minor hiccups in your network. And in general, this timeout should be based on the properties of your local fabric. It's going to be related to things like the size of your fabric, the amount of congestion you tend to see in your fabric, things like that. Its primary purpose is try to distinguish between real, you want to distinguish real hardware-related failures. Set it low enough to detect those, but high enough that you're not hit just because a user job submitted a few too many requests and caused a little congestion on your fabric. And recommendations from this for this are widely varied. It's hard for me to give a specific, value because it varies by the fabric. You search online, you'll see recommendations that vary anywhere from 10 seconds to 100 seconds. One other timeout with the KO2IBLND is the peer timeout, and this is used to determine when a peer is down. It defaults to 180 seconds. The default value comes from the generic LNet layer, but if you set this value at the KO2IBLND level, it will actually propagate up to the generic LNet layer too. According to the Lustre manual, this is you would, if you had a routed environment, you would set this on the routers, but not on the clients and servers. But if you don't use routers, there can be some benefit from actually enabling it on them. And in general, you want to make sure that this is not less than your LND timeout, because you don't want to consider, if at the LND layer, if you don't time out a request, you certainly don't want to time out a peer because they responded in less time than a request would take on your fabric. And if you set the keep alive option, the recommendation is that you set the peer timeout to be twice the keep alive timeout. So in summary, timeouts are key to ensuring Lustre resiliency. Optimal values, I haven't given optimal values here because it's not something I can really do. They tend to be very system specific. Although if you run adaptive timeouts, which is the default anymore for recent versions of Lustre, you can avoid a lot of need for some of this tuning. But if for some reason you need to set static timeouts, then hopefully knowing some of these relationships between the values can be useful for choosing a value that's appropriate for your system. And oftentimes to pick the right value, it just comes down to trial and error. And there are way more timeouts in the Lustre code than what I've covered here. So if you're interested in learning more, you can check the Lustre manual has information about some more of these, and just digging into the source code, you'll find out where a lot of these are identified in there. Just a general acknowledgement for the OLCF computing facility, and I'll be happy to answer any questions anybody has.
Questions? Hand over this way.
Hello. I had a question about, have you done any correlation between the jobs that you want to run on a cluster against how the timeouts get configured? If you're thinking about the static timers and how you want to adjust that versus going with the decision of using dynamic timeouts, are they in any way correlated to the jobs that are running on the cluster? And has there been any analysis on that?
I've not done any analysis on it. I think this would be a scenario where adaptive timeouts would have the advantage, because based on your workload, you might see the amount of time it takes to service a request could change based on what's being run, and I think that's where adaptive timeouts would definitely have a benefit there, because they could adjust that value and notify clients as opposed to a static timeout. I think it would be much harder to set a value that could accommodate various types of jobs, or probably more likely is the value you would have to set to accommodate all of them would be larger than what you might typically want to run. It might have to be unnecessarily large, which would take it longer to detect some of these failures or things to time out and fail over.
Thanks.
So I had a brief comment on that. Since timeouts are mostly for sort of failure handling, it tends not to be super job dependent. It's more often like architecture and size dependent and things like that, based on the system size. It's about handling a failure. But I also wanted to say thank you. This is a really nice breakdown of the timeouts, which are really important and can be a real nightmare on large systems. So
Yeah, thank you.
Hi there. Thanks. My question actually is almost sort of already answered. I wanted to ask you whether you think the timeouts are more correlated to the fabric that you're running on, or whether they're more closely correlated to tuning around the job. And it sort of sounds like it's probably closer to the fabric, but definitely not certain. Would you like to comment on that?
Yeah, I think your tuning is probably going to be related more to your hardware, your storage hardware, your fabric, things like that. That's primarily what you're detecting. Is it's guarding against failures in that sort of thing, as opposed to setting a value that can accommodate all the weird behavior that every user might use. In my experience, the times I've seen things that are sort of user-related timeouts has been more of things like users doing stuff that causes, I've seen things with like client evictions related to like whatever the clients are doing on the compute node itself, actually overloading it and driving it so hard that Lustre fails to respond to a callback in time and ends up getting like a client evicted or something like that. But yeah, I don't think it's very reasonable to try to set timeouts to accommodate every edge case user behavior type things. You want to focus it mainly on the hardware itself.
I think what you're also saying was maybe jobs are indirectly related because a bad user job could then cause your fabric to be in a bad state, and your fabric being in a bad state then triggers the timeouts.
Yeah, I mean, yeah, a user can always do things and swamp a system with IO requests and bog things down, and you do that and create a situation where potentially there would be a timeout value or a timeout occurs, but you don't want to just set this enormously long timeout to try to guard against that, because you're really trying to detect the failures. An abnormal situation, I think, in the hardware more so than an abnormal user's job.
Just call our users weird.
All users are weird. Their whole purpose is to destroy your system, especially the storage part of it.
We are not recording this, are we?
Let's thank our speaker. I'm not saying it's intentional, it's just what they do.
Thank you.